about why all this is well, I call it a fusion hype or fusion illusions or so. I have worked since many years on the issue, and it's actually is kind of more and more shocking what happens. Um, just one thing. How can I get this away? Okay. All right. Um, so I have just put a few things together on this, and there, especially during the last couple of months, there's all of a sudden a big hype, especially in Germany, but I believe it's also in many other countries. And I have collected a few headlines, but I would like to, well, have the opportunity to go a bit more in detail, as Hannes said we should do this at some point. Well, I have lots of information on this and collected since something like 20 years now. But I would like first to start with a sort of in December 2022, there was a big announcement, which you could read sort of almost everywhere from a press conference. Historic explosion in the Lawrence Livermore Laboratory, the military research center. And they claim to have net energy gain with laser-powered approach. And this made big headlines. And in fact, they said, okay, at this laboratory on 5th of December, focusing 2.5 megajoule of laser light onto a tiny capsule of fusion fuel and sparking an explosion that produced 3.15 million joules of energy, the equivalent of about 3 sticks of dynamite. Now, actually, in case, how much is 3.6 megajoule of energy? If you take 1 kilowatt hour, which, well, we all use basically every day, or even more, this is just a little bit less than 1 kilowatt hour energy. So you can say this is fantastic or maybe not. But sort of then it became very silent again. But then with the new government in Germany, they had on their not only on the party program for the election, but then in the government program that they want to build the first fusion reactor in Germany, and that they will invest lots and lots of money, actually 2 billion euro by 2029, to support fusion research and development of pilot projects. Oops. Okay, so let me go a little bit, because this is also very much related to our Science for Peace thing. And if you have not read it, I highly recommend to read this article in the Bulletin of Atomic Scientists, which was written also in December, right after the press conference. And it was an interview with Bob Rosner, a physicist at University of Chicago, former director, Argonne National Laboratory, and he was a long member of Bulletin's Science and Security Board. And he said, well, I should tell you that I had some very interesting interactions. I was, for example, on public TV in Chicago, and basically the bottom line is that the Department of Energy publicity machine really wanted to steer away from the weapons part of the story and focus on, the energy future. And if you just probe, if you probe just a micron beneath the skin of that story, you discover that it's not quite what's going on. But I was faced by a TV reporter who thought this is an energy story, and I had to basically tell him, no, it isn't. In short, the problem is really much more difficult. And this facility can be used to train the next generations of weapon designers. You can regard it as a teaching facility for the next generation. So what they managed in this laser approach is basically to test the functionality of nuclear weapons without testing them. So I highly recommend really to read this article, where you can click on the link, I think, in the slides which Hannes has. Now, the other big project ongoing is, as we all know, the ITER project, and something on the status in 2026. But I found an article this afternoon from BBC 2017 where it says the project has been beset by delays and cost overruns, originally foreseen to switch on in 2016, and the construction cost around 5 billion euros, and then they wanted to have another 5 billion euros for the next 20 or 30 years of experimentation. But its price has roughly quadrupled and its startup pushed back to 2025. Full-scale experiments are now not foreseen until at least 2035. Well, this was in 2017 and before all these other disasters which happened. But the headline was fusion energy pushed back beyond 2015. And then if you go for ITER news on 2022, there was an article also, the 20 billion euro project, now 20 billion already, faces delays as defects found in two key first-of-a-kind components. This was made public in November 22. By the way, just a few days before the press conference on the laser fusion happened. And they said in this statement, problems will require in-depth examination and time and budget to repair. And if you look at the latest update from how this is today on the ITER website, well, already you have problems finding what they actually really want to do. But they even don't mention deuterium tritium experiments in the moment. And they hope for integrated commissioning 2033 to 2034, and eventually start some experiments to heat up some plasma by 2034. So another kind of 10 years delay. All right, so let's just one short mentioning of what I found when I looked into it, this absolutely unsolvable tritium problem for nuclear fusion. And just to remind you, I can go in more details, but this would go into some details of cross sections and so on. So the only reaction which one can imagine, and this is also used in the hydrogen bomb, deuterium plus tritium gives helium plus with a certain energy and a neutron with 14 MeV. And tritium with a half-life of 12.3 years is obviously a problem also for nuclear weapons, which have been constructed maybe 20 years ago, and this tritium has to be somewhat replaced in order to function. So I think this is one area where they would like to know if their bombs are still functioning. This is laser testing. Anyway, so the propaganda idea is neutron plus lithium-6 gives you helium plus tritium plus 4.8 MeV with a certain cross-section, and lithium-7, which is 94% actually, or 93% of natural lithium, so it's not very useful, but lithium-6, yes. And then one talks to enrich lithium-6 and so on and so forth, which makes things very, very tricky. And I would like to go in more details at some other point in this whole, what is known and what is basically unknown about this whole breeding. But when you think that sort of every neutron which is produced has to produce somewhat more than one tritium atom, and not only this, but there are unavoidable neutron losses, and it's not only the neutron lifetime. If you think about a tokamak geometry, which must have a size of something like a few thousand cubic meter, and the lithium, whatever blanket imagined, to have a perfect surrounding, and you need a sort of thick lithium blanket. So it's not really a blanket, it should be something like a meter thick in order to have a sufficient absorption of the neutrons and the tritium production. But in addition, there are unavoidable tritium losses, tritium decay, tritium extraction losses. Well, this is a chemistry problem. Tritium is exactly behaving like hydrogen, which has lots of other interesting problems from the chemistry. And I don't know, hydrogen plus lithium is also a little tricky thing when you think about lithium batteries being transported in planes and so on. Then, of course, there are losses when you get the tritium isolated atoms out of this big lithium zone and so on and so forth. And furthermore, there is inefficient tritium burnup. So in the moment, I think it's 1 in 10,000 tritium atoms, which was fusioned in these kind of test experiments from the ones which were put in. Okay, and this brings me to somewhat what I would like to go in detail at some other point. So I think there are absolutely fundamental showstoppers for controlled nuclear fusion on our planet. So when you think a commercial energy production needs a steady state, a permanently function gigawatt electric power plant, and this should operate for years and not for minutes, then we know that there is basically no material which exists which can stand extremely high temperature plasma eruptions. Well, think about boiling water and these bubbles which from time to time explode. So it must be kind of very similar. But it should not absorb any single neutron. So either it must be very thick and at the same time very thin. And obviously, such a material cannot even be developed and tested at on and for ITER at basically no facility. And there were some little few experiments done, and they were a total failure, but nobody is talking about this. Then think about hypothetical 3 gigawatt thermal reactor. When such an just theoretical requires about a fusion of at least 200 kilogram tritium per year. So this includes then the thermal to mechanical energy conversion or moving a turbine basically. And so 1 gigawatt reactor requires something like 200 kilogram tritium per year. And world inventory in 2027 is at best 30 kilogram. Now, all this is basically hidden and never talked about. And people talk at best that they want to have some certain plasma temperature of some, I don't know, 10 to 100,000 degree Kelvin or something. What do I say? 150,000 degree or something. Now, think about nuclear fission power today in the entire world is less than 300 gigawatt electric, and thus roughly 1,000 gigawatt thermal. And this makes only 9% of world's electric energy. So even if you have a very tiny fusion reactor, it is basically nothing compared to our energy hunger which we have. Now, in addition, I think all today's knowledge shows absolutely by first principles, and every physicist can understand this if he or she looks into this. Self-sufficient tritium fusion breeding reaction is absolutely impossible. So as a result, ITER project and all the other 20 millions and growing by about 1 billion per year is at best an interesting plasma physics project, but has absolutely nothing to do with energy research. And for this laser business, it has also nothing to do with energy research, but is basically only for the military testing of functioning of hydrogen bombs. So personally, I would prefer that these hydrogen bombs do not function when they are used, and this use is somewhat coming closer to our minds. So there are also lots of other issues about this, but I think I want to stop now. This was just supposed to be a short introduction.
Thanks very much, Michael.